This is example 1 in module 10, which is about current that's induced in a loop of wire that moves through a uniform magnetic field. So we have a rectangular loop of wire. Initially it is not in a magnetic field, and then it's being pushed into a uniform magnetic field. The first question is asking us to determine the direction that current will run through the loop. So to determine the direction, we're going to use Lenz's law. And Lenz's law basically says that when the magnetic flux through a current loop or through a conducting loop changes, it will induce a current in that loop. That current will then produce an induced magnetic field, and that induced magnetic field will point in a direction that tries to maintain constant flux, or in other words, it tries to counter the change in flux. So in this example, we have a magnetic field that points into the board. If I take this loop and I push it into the field, I am going to have magnetic field lines that go through that loop into the board. So that means that the induced magnetic field is going to point out of the board. It's going to try to cancel the increase in magnetic flux into the board, and to do that, it's going to produce a magnetic field that points out of the board. So now I have a right-hand rule. Well, if I knew the direction of current through the loop, I would curl my fingers in the direction of that current, and my thumb would point in the direction of the magnetic field that's created by that current. So we just need to go backwards in this case. So we know that the induced magnetic field is going to point out of the board. If I point my thumb in the direction of the induced magnetic field, my fingers curl counterclockwise. So the current runs counterclockwise. The second part asks us to determine what the magnitude of this current is. So to determine the magnitude of the current, we're going to use Faraday's law. We know that Faraday's law gives us the induced EMF. If I take a coil that contains possibly more than one loop, change the magnetic flux through that coil over some amount of time. So we have a single loop, which means that N is going to be equal to 1 here. If we had multiple loops stacked on top of each other, we would have to multiply by the number of loops. We need to figure out what is the change in magnetic flux. And we need to determine what the change in time that this occurs, or the time over which this change in magnetic flux occurs. Alright, so recall that the magnetic flux is defined as magnetic field strength times area of the loop times cosine of the angle between the loop perpendicular and the magnetic field. And we're told to assume that the magnetic field is perpendicular to the plane of the loop. That means that the loop perpendicular and the magnetic field are in the same direction, or, well, the angle between them is 0. So we're going to say theta is equal to 0 degrees, which means that cosine of theta is going to be equal to 1. Alright, and the magnetic field strength is given to us in the figure, so we need to figure out what the area of the loop is. So the total area of the loop is going to be its length times its width. So now we need to figure out what the change in flux is, and the time over which this change in flux occurs. Now I will mention that I'm using, so there's a negative sign that goes in front of Faraday's law. Alright, in the book you see a negative sign there. We're looking for the magnitude of the current, so we can drop this negative sign. This negative sign will indicate the direction of the EMF and the current that is driven through the loop. So really, since we're just going to use Lenz's law to determine the direction for all of these problems, we can drop that negative sign. That negative sign is only important if we want to determine the direction from Faraday's law. Alright, so to determine the change in flux, I'm going to write down what the flux is at some initial time. This is right before it goes into the magnetic field. And this occurs at, let's just set the stopwatch to equal 0 at that time. So at time t equals 0, the loop is not in the magnetic field, so the flux is going to be 0. And now I want to look at the flux right after the entire loop has gone into the field. So if I draw a picture of what we have here, this is right before the loop goes into the field, and then this is after the loop goes into the field. So now the loop is entirely in the field. So the magnetic flux then is going to be the magnetic field strength times the area of the loop times cosine of the angle between the magnetic field and the loop perpendicular, which is 1. And this is going to happen, well, this is going to happen right when the entire loop enters the magnetic field. How long or when will that happen? Well, if I say that at time t equals 0, the front edge of the loop is just getting ready to enter the field, then basically what I need to know is at what time will the back edge go into the field. So how long does it take the back edge to get to the line where the magnetic field begins? And we know how far the back edge has to travel. It's just going to travel a distance L. And we know how fast it's traveling. It's traveling with some speed v, so we can calculate what that time is going to be. So that time is going to be the distance that's traveled divided by the velocity. Alright, so then if we look at our deltas, we can calculate what delta t is now. It's going to be t final minus t initial, so that'll be L over v. Same thing with the magnetic flux. It'll be the flux final minus the flux initial, which is just going to be B, L, W. And then I use Faraday's law, and I'm, again, not using the negative sign here because I want the magnitude of the current, which is always a positive number. And the number of loops is 1 here, so that's going to be change in flux over change in time, which is going to be BLW over LV. So the L is going to cancel. And there's the induced EMF. Now, if I have an induced EMF, I can drive current through a resistor. And conductors are resistors that have very small resistances. So the current is going to be given by Ohm's law, which will be the induced EMF divided by the resistance. And we're told that the resistance of the loop is some number, right? Capital R. So that means that the current is going to be the EMF that's induced in the loop, which depends on the velocity, divided by R. And we know that this is going to go counterclockwise.